All right, in this worked example, we're taking a look at question number 12 here, and it reads, a star has a luminosity that is known to be 4.8 by 10 to the 29 watts. A scientist observing the star finds that the radiant flux intensity of light received on Earth from the star is 2.6 nanowatts per square meter. Name the term used to describe an astronomical object that has known luminosity. So this is actually the title of this in the grade book, the standard candle quiz. So we call that a standard candle. And the calculation here says determine the distance of the star from Earth. Slide this over here. All right, so the equation that we need to solve this relates distance, flux, and luminosity. And we've got that the flux is equal to the true power, the luminosity, divided by the surface area of a sphere, right? So the further away we are, the weaker that light appears to us. That's why it's only nanowatts of radiant flux when it's 10 to the 29 watts emitted from the star, right? We're spreading it out over a very large sphere because we're a long ways away, here on Earth from distant stars, from other stars. All right, plugging in the values here, we've got 4.8 by 10 to the 29 watts is the luminosity divided by, let's see, we're solving for distance. So we should actually done here is, let's take a step back. I like doing my algebra with letters first and then working with the numbers. And if you're like, well, I like my math with numbers, you'll eventually get to the point where you're like, I don't want to write all those numbers out. Let's just use a letter that stands for it. So I'm going to change spots, the d squared and the flux over here. The old 1-2 algebra switcheroo. And then take the square root of both sides. So I've got the distance here, the thing I want to know, equal to the luminosity over 4 pi times the flux raised to the 1/2 power, right? Same thing as taking a square root. So then that's going to be, I'll substitute now, 4.8 by 10 to the 29 watts over 4 pi, and you have 2.6 nano is 10 to the -9, right? Billionths. So 2.6 nanowatts per meter squared. Here we see that watts is going to cancel. And once we take the square root of all of that or raise it to the 1/2 power, we're just going to get meters of distance. All right, sure thing, YouTube. You want to see that calculated on the screen? No problem. Here you go. We've got 4.8 times 10. Let's see, raised to the 29. All right, so in standard form, you see it in all its glory there. That's a lot of watts. Divided by 4 equals, divided by pi equals, divided by open parentheses. So important, 2.6 by 10 to the -9 equals, I have something to the 37th power, which, we know space is vast, but that's really vast. So don't forget to take the square root there when we get this answer. The distance equals, I'm going to go ahead and change this over to exponential form. And so we get in the calculator 3.83 times 10 to the 18 meters. I think in class we converted that into light years. Remember that there's about 10 to the 15 meters, 9.45, by 10 to the 15 meters in a light year. So you can convert that into light years or parsecs or something to make better sense of it. All right, the question goes on to read, the sun has a surface temperature of 5,800 Kelvin. The wavelength maximum of light for which the maximum rate of emission occurs from the sun is 500 nanometers. The scientist observing the star in A finds that the wavelength for which the maximum rate of emission occurs from the star is 430 nanometers. Show that the surface temperature of the star in A is approximately 6,700. So at a shorter wavelength, it's going to peak at a higher temperature. And that's because the wavelength is inversely proportional to temperature like that. So if we want to sort of show that the temperature of a star is something, we'll take a ratio of the temperatures like this. This will be the temperature of the sun. The wavelength of the sun is going to then be, sort of the numerator over here. And we've got that as 500 nanometers. The temperature that we want to show is 6,700, corresponding to the distant star, which peaks at 430 nanometers. All right, so I'm plugging in 5,800 Kelvin for the sun. Solving that, you can show that the temperature is 500 over 430 times 5,800. You get 6,744, which is indeed about 6,700. Use the information in A and B1 to determine the radius of the star. Well, first, I think what I'll do is let the bell ring, and then I'll finish off that calculation. But I'm not going to pause the video in between. We want to hear what the bells sound like here in the 21st century. All right, have a good day, students. I'm going to continue on with this part 2 here. All right, so we've got the Stefan Boltzmann equation here, and we want to use the luminosity from part 1, which was 10 to the 29 watts. Actually, 4.8 by 10 to the 29 watts. All right, and then the radius of the star is going to be sort of from the area term. So we got 4 pi r squared is the area, Stefan Boltzmann constant, temperature to the 4th power equals the luminosity. So likewise, so we did in the other calculation, we're going to isolate r, the radius. And so that's going to be L over 4 pi sigma t to the 4th. And then we got to take the square root of all of that. So substituting in some values now, we have 4.8 by 10 to the 29 watts over 4 pi sigma. Stefan Boltzmann constant is 5.67 by 10 to the negative 8. And the units are, let's see, watts per meter squared per Kelvin to the 4th. And then the temperature for this, the distant star, you may recall, was 6,744, about 6,700. So we have to raise that to the 4th power. And then take the square root of all of that. All right, I'm going to work through this on the calculator too. So typing all this in here, we've got 4.8 times 10 raised to the 29th power. Oh, you did that, right? So that's the numerator there, divided by 4 equals, divided by pi equals, divided by Stefan Boltzmann constant, 5.67 times 10 raised to the negative 8. And then divided by the temperature of the star, 6,700. Remember, it's a high power law, so that one is raised to the 4th power. So you get an answer there, but remember, all of that is underneath the radical, and so we want to take the square root of that. So here we're solving the radius. I don't know if I trust this answer. 18,284,140. 582, we'll round that to a 3. Should probably round it here, but this is, let's see, in meters, billions of meters. I feel like maybe when we typed that in, we went wrong somewhere. So let's type it in again. Maybe you saw the mistake. If you did, leave it down in the comments below. I'm going to check it again. 4.8 by 10 to the 29. divided by 4 equals divided by pi equals divided by Stefan Boltzmann constant 5.67 times 10 to the negative 8 equals divided by 6,700 to the 4th, close parentheses, equals square root. Yep, so we do get that number. We checked it twice. That's the warning bell. So that means class is about to start for the next period here. So let's finish this one off here. We'll toggle it over to scientific notation. And we're getting 1.83 by 10 to the 10 meters would be the radius of that distant star. All right, so this was the standard candle quiz, the working on it, and another worked example with Dr. Schleich. We'll see you next time.